Some more IP tables and adding stuff today. I didn't. I was thinking about it more a little bit on Wednesday from our conversation about how you could kind of set up a pseudo LAN type thing. Um, and I want to go into that a little bit more now. I looked at it some more, and it turns out the way we had set it up wasn't very secure at all. And we're going to talk about what you can do with the setup that we had previously. Um, that actually is kind of interesting, and we're going to talk about some interesting things around that and why it works out. And then we're also going to talk about the LAN services, things like DNS, DHCP, that will give us a kind of a full router suite of things to do. And we talked about that on Wednesday. On Wednesday, we just had right now we still do. We have a client that's statically IP'd inside of this little LAN network. I guess I have the diagram over here too. So again, we have this Ubuntu client connected to Ubuntu 1, and then Ubuntu 2 or 1 is connected to our main network. And again, we're adding traffic from Ubuntu client through Ubuntu 1 right now. And remember what that looks like when we're adding traffic through something. This is 2.100. This has this interface right here is 2.1, and then our main network is, don't ignore the IP addresses in the ILab, by the way, those are off, and our main network is 1.21. So when we're sending traffic from, let's say, Ubuntu client to our pfSense box, it will essentially have the IP address of Ubuntu 1 as it's going through. So again, we know the route back to Ubuntu 1, so that's the whole reason we're adding things, is there's no route back through Ubuntu 1 to Ubuntu client. And we're going to talk about some manual route stuff that we're going to do, and that's kind of how we're going to think about the security aspects of things. So go over to Ubuntu 1 really quick, just take a look at the IP tables. So completely open right now, IP tables, LTNAT, specifically see the NAT chains. See we have that masquerade there. So if I go over to Ubuntu client and I ping 192.168.1.1, everything works out perfectly fine because we do have those masquerade rules. Hey, Hunter, Cole, stop. Bad. Okay. But what's interesting about all of this is without any rules in the forwarding chain, what we can actually do is forward arbitrary traffic through Ubuntu 1, this router. And the way we're going to demonstrate that is by setting a route for this LAN network, this 192.168.2.0, manually in whatever device we want to use. So if I was to go over to my Xubuntu box, just an arbitrary client on our network, and I was to ping 192.168.2.100, which is my Ubuntu client right now, obviously we're not going to get anything. If we look at our route, there's a couple different ways we can look at our routes. So hopefully we have the traditional netstat RN, and you can see I got a default route to 192.168.1.1, and in this case, since we don't have any specific routes to that 2 network, everything is going to be pushed to our gateway, but the gateway doesn't know where to put it. It's probably going to forward it on kind of into the ILab infrastructure, but we don't really care, we don't really know, it doesn't really matter. So anyway, what's interesting is, again, we can add a specific route to push traffic going to that 2 network, specifically to Ubuntu 1. Okay, so the command to do that, we can add routes. You could do it kind of the old way with route add. The new way is a little bit more easy to use. You just say IP route add, and then you say what your route is, and then your subnet, and then you say via a particular host. And any traffic that's hopefully this is obvious right now. with networking experience, with routing experience and everything like that, is when we say via like this, it will do an ARP lookup, it will find the MAC address of that, it will set the destination MAC address to the MAC address of that host, and it will push the entire IP packet frame thingy to that host. So it won't really look any different if we were to TCP dump the output, at least the traffic that's being generated from the XUbuntu box. It won't look any different, but it'll be sent to a different place, at least from a TCP dump standpoint. If we were to look at it in Wireshark, or actually look at any of the MAC addresses, obviously it would be pushed to that host. So we run that, and now when we go back and ping 268.2.100, you can see traffic is actually being routed all the way through, which is interesting. And I think it's very interesting to think about why all of this actually works out. So from a very basic standpoint, the traffic is going to the router, the Ubuntu One, and the Ubuntu One is then just sending it to the LAN network. And what's interesting about this, I think, is also there's no explicit routes on our secondary LAN network. When I'm referring to LAN, I'm kind of referring to it as all of this stuff that we're working on here. And on that network, there's no explicit routes back to where the packet came from. If I was to TCP dump this here on Ubuntu client, ICMP, and then ping it, you can see that the source IP is on that one network, as expected. And all the routing is taken care of by the default gateway. And everything that we don't have is just sent back to the Ubuntu One router, and then the Ubuntu One router has a route to back to our XUbuntu box. But again, this isn't something that we really want to allow by default. We don't want arbitrary computers on our other network to be able to just get into our LAN. That's something we'd want to more explicitly configure and allow only on an as-needed basis, kind of the port forwarding things that you think about with your LAN networks. So what we're going to do is tinker with our IP tables rules a little bit more. Remember this diagram right here? I really cannot stress enough how important this diagram is to understanding things. I was working with IP tables for a very long time and kind of was just copying and pasting commands that would do things. But this diagram really helps, and helps you understand what's being processed and what's actually happening. So again, we had one post routing rule for NAT, and that was the source NAT, and it would source NAT it through Ubuntu One, and the source IP would then be Ubuntu One's. And as long as we're using, there's actually a source NAT kind of component to IP tables, and there's a masquerade component. We want to prefer the masquerade rule, so J masquerade when we did it before, because it manages a lot of different natting things just behind the scenes. We'd have to explicitly manage otherwise, which are just kind of annoying. But again, that's the only rule we have right now, is outbound traffic from our inner LAN will be masqueraded to the IP of our router. So we're going to look at these forward rules here a little bit. And it's important to remember again that the forward rules are only applying to traffic that is moving through the device. Remember, if traffic is heading directly for the device, it just comes in like this and goes to in. So just important to remember that. And traffic going through again, it hits pre, hits forward, hits post, and those are the ones that it hits. So let's just look at forward. I think I have the rules right over here. So we're going to change the default policy to drop. If we were to do nothing except for change the default policy to drop, all traffic would be dropped regardless of our other rules. And then basically what we're going to do is traffic originating from our inner LAN, we're just going to unconditionally accept it. And then traffic originating from our our outside LAN, we're going to only accept it if it is related or established. So traffic or session traffic that originally originated from our inner LAN. So this is Kind of interesting. So let's go ahead and do that and then demonstrate what's changed in all of this. So we'll say IP tables, A input, or sorry, forward, or let's do the policy first. So default on forward, drop, IP tables, A forward, ENS34, J accept, tables A forward, ENS30, oh shoot, did I do that the wrong way around? Sure did. Okay. Got to fix that first. I did the wrong interface, so that's going to break things. Tables, L, line numbers, IP tables, D, forward, and then our line number, delete that one. Now let's go back up to my history, find that, switch it to 34, and then we have the related established from our outside LAN. And I really should be calling that network the LAN, but since we have other things over there, I haven't really committed to doing that yet. I think I say long option state. All right. So let's go over to Ubuntu client. Let's just make sure that things are still working. So I'll ping the router. Traffic is still flowing through perfectly fine. But now if I was to go, I hope everything works according to plan. If I was to go over to my Ubuntu box now, I don't believe that I would be able to ping that anymore. Nope, so we can see that traffic is being dropped and only related and existing sessions are actually being allowed in. So that's exactly the thing that we would normally want to do. So again, the full spectrum of what we want to do to enable IP forwarding, NAT, all of that stuff is enable IP forwarding in the kernel, turn on masquerading in the post-routing rule section, and then we want to go into forwarding and only allow basically outbound traffic to be forwarded and responses to outbound traffic to be forwarded. So in that case, I think it's also relevant to look at port forwarding really quick and seeing how we could do that. I don't really know how much time I want to spend on it. Nothing that you can't really just look up and do later. But basically, I'm just going to kind of explain what is happening in all of these commands instead of actually doing them. So in order for traffic to go through forward, we would just have another rule on forward that would actually allow traffic from a specific host to another. So basically forward, we look at, I don't know why this command has state in it. I don't think it actually would be required, but we'd say protocol destination to 100, and then the port, and then we'd accept. But the more important part is this pre-routing DNAT part. So basically this says when something's coming in on pre-routing, destined for port 8080, we would destination NAT it so it looks like this. So if we were to send traffic directly to, this is slightly different than what was happening before. Before, traffic was being routed through Ubuntu 1. It was explicitly by the client addressed for Ubuntu client. So Xubuntu was specifically saying 2.100 and it was sending things. So with port forwarding, of course, it would be slightly different. We would address it for the router, and then the router would use destination NATing to change the actual destination address. And the destination address would then point to our inner network. And then it's also important to remember that our forwarding rule actually needs to say, the destination of our inner LAN. And the forwarding rule wouldn't say the destination of the router, because remember, as things are being processed here, we have pre, and we're looking at the pre chain right now in pre-routing. It would change it there, and then in order to match that again in forwarding, we would actually have to look at the new packet instead of the old one. And it's kind of interesting actually, so we might as well just go ahead and do it. I'm going to try and do it with ICMP, because it should theoretically be a little bit easier. So yeah. Alright, so what we do is like this. I'll clear this out. IP tables. I'll say PICMP, and then destination 192.168 2.100 J accept. I need to actually append it to input. Think about this for a second. And then we would go in NAT, a pre-routing. Should have done these rules in the other order because that's the way they'd be processed. PICMP, and then JDNAT, to destination, and then our IP address. Spelt it wrong, it said DNAP, not DNAT. And there we go. And this is actually a very terrible example because by default, if I was to ping Ubuntu 1, Ubuntu 1 would respond. And all of this, what's probably going to happen, it's kind of undefined actually, but what I would hope to happen is the traffic comes in and it looks like Ubuntu 1 is responding, but Ubuntu client is actually responding. And we should have done the TCP example, and it would probably been better, but no reason to go back and change now. So, ping 192.168, 21.1, not 21.1, 1.21, wrong way around. And of course now we're not even getting responses. Now I'm just going to debug this, think about this for a little bit here, and then we'll move on back to what I actually originally intended to work on. So TCP.py, EMS34 should be our secondary. Traffic's coming in. I think the only point of failure is actually the forwarding rule. The source, the IP address, IP addresses I might have mistyped those. And I don't think I actually got the forwarding rule in here. I don't see it. Oh, I put it in input and not forward. Obviously, that's not going to work. So, pre-routing changes the IP address, and then since I no longer matched input anymore, it went down the forwarding chain. Or table, or whatever you want to call it. So now, theoretically, if I go back over to Ubuntu, now we're getting ping responses, but it's also important to remember again that these responses are being forwarded to Ubuntu client, and Ubuntu 1's not actually even responding. Again, should have done the TCP example because it would have been explicit, but didn't do it, whatever. So that's just some thoughts on port forwarding and everything. So, okay, so I'm actually going to go in and clear most of that out, I think. It doesn't even matter, it's just ICMP. So we'll just leave that as is, and let's talk about DHCP and DNS. So we have our NAT right now. I'm kind of thinking of the typical home router setup right now, just a very simple example. So the services that your home router provides would be this NAT. So your ISP would give you a WAN address, and you would only have one IP address, and you have a bunch of clients, of course, inside your inner LAN. And those clients want to talk to the internet, so you got a NAT through the router. And we have that working right now, but the router would also provide DHCP, so when your clients connect to the network, they would be given an IP address automatically, and odds are it also provide a DNS server, resolver, cache type thing. It's interesting to think about all of that. And there's kind of two setups that we could go for here. I'm going to use DNS mask, and that's kind of for a simpler network, kind of LAN type thing. Larger address, you might run a full DHCP server, so DHCP-D, or bind, in addition to bind, which is a more complex DNS server. But DNS mask should get us along just fine, I think. So super simple to add these services to your network. We're going to Ubuntu One here, install DNS mask. All right, and then there's a couple options I'm going to configure right away, and then I'll come back and look at some more of the more complex options. So at the very minimum, what I want to do is specifically bind DNS mask to our inner LAN IP address, and then turn on DHCP. So by default, DNS mask is just DNS, kind of used as a local DNS cache a lot of the times. So it's worth talking about a DNS cache too, I guess, if you haven't thought about that much before. The whole reason you'd want a DNS cache on your LAN, on your local computer even, is lots of DNS requests. You don't necessarily always want to duplicate them. DNS records don't necessarily change all the time either. So there's no reason for you to be doing a DNS lookup, at least over the WAN, which might be up to 100 milliseconds, 300 milliseconds of latency, all the way to the DNS server to look up Google a million times. So what your router might do is cache that response, and then continuously, when your client looks it up, instead of the client, your router, and then the internet, instead of going all the way to the internet every time, if it just has the same response, it would just go to the router over and over and over again, obviously. So, but anyway, let's change the bind address to our inner LAN and then turn on DHCP. So we go over to dnsmask.conf, I believe, and then we will look for a listen address. It's listen dash address. And we'll go ahead and uncomment that, and we'll say we want to listen on 192.168.2.1. Again, now we just have DNS listening there, but of course we want DHCP too, so I'm going to go search for DHCP range, I believe. I spelled that wrong. DHCP range. And this is the only thing that we actually explicitly have to uncomment to allow DHCP. So we're going to uncomment the DHCP range. There's a couple options we have here. So this is the IP address that we start at for where we're going to give DHCP addresses to, and this is the address that we finish at. So obviously those IP addresses aren't right now, so we need to go and change those to be whatever we want them to be. So we'd set 192.168.250, and then we'll say through 2.99. And then the final option is the length of the lease. 12 hours is pretty good. So every 12 hours, if your client's connected, it would try and acquire a new lease every 12 hours, or perhaps under other circumstances. All right, so that's all we do there. DNS mask. And then let's look and see what's running. L and P. We'll look at UDP first. So we have DNS mask listening on 53, so we have DNS for sure. And I'm not quite so sure that we have DHCP actually functioning. It might have already been started, so I'll actually restart it. So I think DNS. What port is DHCP on? What, like 60, 69 or something? Anybody? Port for DHCP? Anyone? All right, so yeah, so it was already started. That's why what was happening here is it was already started. When I started it, it just ignored that. And now that I actually restarted it, then it was actually loading. So we can see we're listening on 6768 there. And my listen address is broken for some reason. I don't know why it's ignoring that, which is annoying. If we have two DHCP servers on the network, it's just going to really, really break things, and I prefer for that not to happen. So I'm going to go back in here, that's resolve.conf, and try and figure out why that's broken right now. It should just be listen address, but clearly it didn't work. I'm gonna try and change this from listen to interface. So ENS34 instead. That might fix it. Just check and make sure it was actually ENS34. Yep, it was ENS34. Restart. And it's still listening everywhere. And that doesn't really make sense why that's happening to me. But we're just going to go with it. For the purposes of the demonstration, it should still work fine. So now we have, hopefully, a DHCP server running. And I have the static IP right now. Again, I'm back over on my Ubuntu client now. Have this static IP of 2.100. And when I run DHClient to get a new IP address, I'm going to say my adapter, and look at it. And see we didn't work at all. I think I actually have DHClient already running, which is going to break things. So run it again. Now we got an IP address, so we can see DHCP retrieved an IP address. Now we're at 2.82. But the also interesting thing is I believe DNS will be working, if I'm correct. Let's just look it up. We can see our server has been set to the router, so 2.1, and that will be caching DNS queries and forwarding them on to whatever DNS server that device had. And we just continue to go down like that. So yeah, super straightforward to actually configure all of that and get your LAN services up and running. So yeah. So all you have to do is hopefully change listen address. I'm still annoyed that didn't work. It should totally have worked. And then uncomment DHCP range to actually get DHCP. So the one thing you might want to change is not using the DNS cache. So you can also configure DNS mask to send DHCP options directly to the clients. And you could say, just use this DHCP server in their DHCP options, and then say port 0 to actually turn off DNS forwarding and resolving and all of that. So again, what's happening right now is DNS is going directly to the router, and the router is forwarding on the requests. In this configuration, the Ubuntu client itself would connect directly to 8.8.8, Google's DNS, and then decide what to do, or then make their query, I guess. So Ubuntu 1, our router, then etc dnsmask.conf. So what I'm going to do is turn off this. So I just say port equals 0, and then DHCP option equals 6. So 6, there's two syntaxes that you could do here. I don't believe there's the named option way and there's the number. So if you go in the RFC and everything, there's different numbers that are associated with these names. 6 is DNS records. For other fields that are named, you could say router and then go on and say things. But I don't think you're actually allowed to actually name the field. You actually have to specify the manual number. So we'll say .8.8.8, restart. Hopefully when we go over to Ubuntu client here, we delete our DHCP lease and renew it. Hopefully this will renew. We should see, hopefully, that our server is now 8.8.8 instead, and we're completely bypassing the DNS of the router, which is something that's actually interesting to do sometimes. And this is all automated, so all of your clients would get the Google DNS server in their DHCP options instead of your local router in your DHCP options. So we can also see that by setting port equal to 0, we no longer have anything listening on 53, no DNS server anymore. So that's how you would go about disabling that, which is, again, kind of interesting, I think. So that's all I have for you today. As usual, feel free to stick around. We have those labs, of course, on disk partitioning and backups, which are due Sunday at midnight. So if you have any questions about those, feel free to ask, I guess. All right.